Hi, this video is an introduction to sound waves. Sound is one of those things that I think we often take for granted because sound is all around us, but if we study sound and we try to figure out what's actually going on, it's amazingly complex, yet at the same time it's incredibly simple and straightforward, predictable, using math and physics. So I'd like to start introducing you to sound in this video by considering a tuning fork. A tuning fork is just a piece of metal that's been bent into a fork, but this is not one that you eat with. Instead, if you strike this tuning fork with a mallet, you'll hear it produce a sound. And when the tuning fork makes a sound, you'll actually hear a high-pitched sound, but there's a lower-pitched sound that is actually more intense. It's just sometimes harder to hear. So I'll show that to you here. I'm going to strike the tuning fork. You'll hear the sound. But if I bring it close to the microphone, you'll hear the actual, the most intense or the highest amplitude sound coming from this tuning fork. So did you hear that? There's a lower note there, and that's the amplitude, that's the frequency, sorry, that this tuning fork is oscillating at. Oscillating just means vibrating back and forth. Now, how does that make a sound wave? All it is just a piece of metal moving back and forth really quickly. Well, the way that it works is if you consider air molecules next to this tuning fork, starts out in equilibrium with nothing really being disturbed. But once you hit the tuning fork, it starts vibrating very quickly. This one vibrates 256 times per second. So that's very fast. It's impossible to see. How it just looks blurry. What happens then if we slowed it down to just focus on what happens as the tuning fork expands, as it vibrates back and forth? It will bump into some of those air molecules. And it creates a compression of air molecules. The air gets compressed into a smaller region, more dense there. So we call that a compression. Okay, that compression gets passed on to other air molecules as they bump into each other. So this first column of air molecules bumps into the second one, and then that second column will bump into the third one, and so on, passing on that disturbance, which is a wave. But the tuning fork's not done because it's got to vibrate or oscillate back, and so it kind of like retracts in a little bit. It goes out and then it comes back in. As it does that, it creates kind of like a vacuum effect, or just a lack of air molecules there. You could say that the air is rare in this region, and the only reason you would say it that way is because this is called a rarefaction. The air is rare there, and so it's the opposite of a compression where there's a lot of air. When there's not as much air, we call it a rarefaction. And so we have, over time, if we let this continue to play out, we'll have a series of rarefactions and compressions, rarefaction, compression, rarefaction, and that's a sound wave. It's a series of compressions and rarefactions, but I like the way that I saw a meme put it. Sound is really just wiggly air, if you think about it. Sound waves are also longitudinal because these air molecules are vibrating to the left and right in this picture, and the sound wave is moving to the right. So if the medium is moving parallel to the wave, we call that a longitudinal wave. And then lastly, sound waves are fast, at least relatively fast for our ordinary objects, because the average speed for this kind of sound wave is 343 meters per second, or that's about 1/5 of a mile per second. So very quick. Sound waves are fast. So let's talk about one other aspect of sound waves that's really essential to understanding sound, and that is the pitch of a sound wave. Now, I've already kind of mentioned it. The frequency of a sound wave is measured by how often the air particles oscillate or vibrate back and forth. 1 vibration per second is equal to 1 hertz. This tuning fork oscillates at 256 times per second. So it'll bump into air molecules 256 times per second. So it's got a frequency of 256 hertz. This is middle C. Higher frequencies sound like a higher pitch. So when I hit this, you'll hear the higher pitch, and that's because there's also another wave acting or moving through this tuning fork at a higher frequency. Two waves can be in the same place at the same time. which that's a concept for another video. But higher frequencies sound like a higher pitch. So how high can we hear? What is the highest note that we can possibly hear? Well, I have here a table of different hearing ranges for different creatures. So humans can hear anything from about 20 hertz to about 20,000 hertz. Now this is these are all just rounded numbers, there's estimates, okay? So different people have different estimates. As you get older, you can't hear it as high as you did before. But we can hear up to 20,000 hertz. Anything that's over 20,000 hertz we call ultrasound, and there are some animals that can hear those kinds of frequencies. For example, dogs can hear up to 45,000 hertz. Cats go up to 85,000, and I've seen some places say that dolphins can hear up to 200,000 hertz. That's ultrasound, ultra high frequencies. And the reason, dolphins can use echolocation. Bats too, they can hear really high frequencies, so they have a use for that kind of hearing. And then I also learned that elephants can actually hear below 20 hertz. They can hear sounds possibly as low as 5 hertz, which to us would not sound like anything. That would just be something moving back and forth like this, vibrating. You don't hear a sound from that, but elephants can hear that sound, apparently. Sound waves that are below 20 hertz are called infrasound. So that's all I've got for you in this video. Remember, humility is not thinking less of yourself, it's thinking of yourself less.